In section 7.3, we cover something called area and the definite integral. In our class, we actually only cover a very small portion of the section, and we mostly look at this section to just get an understanding of what is an integral. And just to talk a little bit about some of the bigger picture ideas of calculus, well, one thing that we've talked about a lot is the derivative. And the derivative, it is essentially the slope or how something is changing. With an integral, we're actually looking at area. So we can use integrals to find the area of things. Since we are going to be talking about area in this section, these are a few area formulas that we're going to use. So area of a rectangle, area of a triangle, and area of a circle. Let's say we have a function negative 2x plus 8, which is where this line here comes from, this diagonal line, and we want to find the area between that line and the x and y axis. So we're trying to find the area that's shaded in green. So right now, what I want us to do is not worry about integrals, but just from what we know about finding areas. So this is a triangle, so we would need to use the formula for finding the area of a triangle, which is 1/2 times base times height. So for this problem, that would be 1/2 times the base would be down here, which is 4, and the height would be this, which is 8. So if we multiply that, we get 16. So we'd say that the area is 16 square units. Now let's look at this example. So again, we're just going to use geometry to find the area between this curve, which is the square root of 6x minus squared, and the x and y axis. So when we have something that looks like this, you may be able to tell from the shape that's given, but we're actually looking at a semicircle here. And the reason that this is what a semicircle would look like is, and we're not going to cover this too much in this class, but just as a quick recap, a circle can be rewritten as a basic circle centered at 0, which this one is not centered at 0. Would be something like x squared plus y squared is equal to the radius squared. So this is the basic equation of a circle. If we tried to write it as isolating y, we'd first get y squared is equal to r squared minus x squared, and then we'd have to take the square root. But the thing is that when you take the square root, when you're solving, you need to do the plus and the minus. And that gives us y is equal to plus minus r squared minus x squared. So the point that I'm trying to get at, though, is that when we actually do have the equation of a circle where you've isolated y, the plus is actually telling you the top half is an equation for the top half of the circle, and the minus is actually telling you the equation for the bottom half of the circle. Now, our equation doesn't look quite like that, and that's actually because this circle is not centered at 0, 0. But I don't want to go into the details of that for this class. But this is the equation of a semicircle. So knowing that, we can actually use the formula for finding the area of a circle to answer this question. So the area of a circle is pi r squared. So that would be the area for the entire circle. If we actually just want half of the circle, we would actually multiply that by 1/2. So let's say if I change this instead to a circle to be a semicircle area, that would be 1/2 pi r squared. So that would be 1/2 pi. And in this case, if we think about the center here, since it goes from 0 to 6, would be at 3. So that means the radius is 3. So that would be 3 squared. So we get, our answer is 9/2 times pi. It does say to round to 1 decimal, so I'll go ahead and plug this into the calculator. And when you plug it in, you should get about 14.1 square units. So now the question is, okay, we've done some geometry, we found areas of shapes. What does this have to do with calculus and integrals? And it has to do with the fact that the integral of a function actually gives you the area under the curve. So we can actually find areas of all kinds of shapes as long as we know the equation of the function on the top. There's a little bit change of wording here because in 7.1 and 7.2 we talk about something called the indefinite integral. So whether we're talking about an indefinite integral or a definite integral, all the rules for integration are the same. The only difference is that when we talk about a definite integral, you'll see that there are numbers on this integral symbol, and the numbers are representing a specific starting point and end point. In the next section, we'll actually talk about how to integrate using those values. In this section, we're still focusing on finding specifically just the area using geometry. For these last two examples in this section, I don't actually want us to use any of the integration rules. I want you to just recognize that that integral is just trying to find the area under this curve. So these are curves that we actually saw in our first two examples. So let's go look back at those. So here we were looking at negative 2x plus 8 as the function between the x and y axis. And if you look, it started at x is equal to 1. I don't know why I said 1, 0. And it ended at x is equal to 4. And so that's why we have the endpoints of this interval from 0 to 4. So we're trying to find the area under the curve, negative 2x plus 8, from 0 to 4. And we already found that area. It was 16. Same thing for this last example. This is actually just like the second example that we did. So this was a semicircle, and it actually went from x is equal to 0 to x is equal to 6. And the area is 9/2 pi. So here we want the area of that function between 0 and 6, which is 9/2 pi, or approximately 14.1.